Hello, I'm going to talk about formalizing OCaml GADT typing in Coq. This is joint work with Shuanruichi. Principality of GADT inference is known to be difficult, but in OCaml, the type system has proven to be principal thanks to a notion of ambivalent types, which allow to detect ambiguity escaping from a branch. Here we see two examples based on a classical witness. In the first example, we are receiving a witness that a is equal to int and use it to type this if expression in which both branches are returning x. And in the case of OCaml, it is assumed to be principal, and this is returning actually a in both branch. On the other hand, OCaml GHE rejects that as ambiguous. On the other hand, if the if expression is changed to return 0 in one case, since x was supposed to be type A, well, the if expression itself is typeable, with a in one case, int in the other. Both are compatible since we have the equations, but since we cannot choose which one we should be returning, this is deemed ambiguous. How is it done? This is types that rely on GADT equations are represented as ambivalent types, which are a form of intersection types. And ambivalent types are only valid when equations are available, but the relation of equations is implicit. And what we are doing here is, well, first we are adding the equation to the environment. Using this equation, we can compare x and 0. That is, x is of type A, but actually it can be seen as type int. And in both cases, we're returning x. And since we are returning x in both cases, actually the return type is just A. On the other hand, here, since we're comparing x with 0, it has to be both A and int. And as a result, we have a current type such that we are receiving something of type alpha, returning something of type alpha. In the other ambiguous case, what happens is actually, since one branch is returning something of type A and the other of type int, we get an ambivalent types of type A and int, which is not valid once we leave the scope of the equation, and we get an error. Actually, OCaml and Haskell differ in their handling of unification under GADT equations. In Haskell, unification under a GADT equation cannot involve variables from outside. This is the outsiding algorithm. On the other hand, in OCaml, this is allowed as long as the equation is not required for the unification. This is ambivalence. The point is that relying on ambivalence is sound with respect to in-place unification, because it tracks whether local unifications are still valid outside. And also, it can ensure principality of inference, because alternative types are going to be rejected. The idea is that in this example, while we could actually in the type system decide that this x is to be seen as int, this will not be not just int, but actually it wouldn't necessarily have to be a and int. And as we've seen here, if the return type is a and int, it will be rejected as ambiguous. So the only possible types is going to be a. Of course, we can still use type annotations to hide the ambivalence by separating in our data types. Here, for instance, we have in one case we decide that the return type is a, in the other case we return that the return types indeed they are both valid. And while here we write the annotation inside, which is correct with respect to type system, OCaml of course allows you to write it outside. Is it really principal? Well, when looking for reduction rules validating subject reduction, we came upon the following example. Where using here two witnesses, one says that A is equal to B arrow B, and the other that A is equal to int arrow int. And we realized that when you do that, actually according to the order in which you use the witnesses, applying G to 3, which necessarily requires using one of the equations, is going to return a different type. In one case, we're returning a B. In the other case, we're returning int. Well, clearly, there is a problem. And by looking carefully, we found a bug in the theory. That is, the ambivalence of G is not propagated to a result of the application of G to 3 and failing to detect the ambiguity. The bug was not really hard to prove, to fix, at least on paper, but we want some guarantees about the correctness. And since we have already proved the soundness and principality for another fragment of OCaml that use a graph representation of types, this is the structural polymorphism about polymorphic variants and object types, actually we thought that we could reuse that for ambivalent typing, which is also a type system based on graph types. Here, how does it work? It's basically that when you have a judgment is also using a kinding environment, which you can see as a graph, that is a mapping from variables, which are node names, to the kinds that are going to describe the nodes. And actually types then are just pointers to something inside the graph. And by enriching the information in kinds with real variable passes, we can represent correctly ambivalence. Principality is still going to be hard to prove, but subject reduction is already a good benchmark for a well-behaved type system, so this has been our first step. Here are the technical part. So the idea is that we want to encode ambivalent types, and here we are going to encode beta to gamma and A. And the way we encode it is through this graph and with a pointer alpha. So alpha is an arrow type with domain beta, codomain gamma. And the ambivalence is denoted because we also indicate that it can also be seen as having type A. And beta and gamma are the children of alpha. They are just variables, but there is a well-formedness constraint which requires that they should get actually the rigid variables. So they get children of the rigid variables. So beta is going to be a.dom and gamma is going to be a.cod. Now looking about all the types we have, actually there are two kinds. There are the graph types, which use this kind of constraints. And there are also three types that we are going to use for equations to make the theory more manageable. Well, three types are basically used only for type annotations and equations, and the graph types are used for everything else: kinding environment, type schemes, typing environments, and substitutions, which are just mapping between variables. Since our types are just variables, they are seen as pointers into a graph. Of course, to make it work, we need some notion of well-formedness. So we have many well-formedness judgments. One is just talk about a kind being well-formed in a kinding environment. In particular, the restriction about children of a node needing to inherit rigid variable paths is part of this notion of well-formedness. In turn, since kinding environment is multi-layer recursive, we define the well-formedness as a kinding environment and the well-formedness of a typing environment. And we have also a notion of validity of a substitution between two kinding environments, which is basically saying that the substitution theta is mapping a morphism of graph. Another judgment we need is an embedding, how to embed a tree type into a graph type. Our terms well, they're just the classical one, extended with type annotation, witness introduction, rigid variable introduction, and witness elimination. And witness elimination, for simplicity, will require explicitly to indicate the equation we are introducing. Now our typing judgment, they're going to use the environment we've described. So the equation environment, kinding environment, typing environment, and the dance environment M as type alpha, which is actually something described inside the kinding environment. And if a typing judgment is available, then this implies that a K is well formed under Q and gamma is well formed under K and Q. Now an example of embedding is the first program we've seen. This can be encoded as this program here. And the main change is that since we do not allow type annotation abstractions, we must either use a let or use the fact that witness elimination as an explicit annotation. So this way we've kept the annotation. Since we don't have if, we just define add something to the environment. So the if pos, which is for all beta into beta to beta to beta. Well, in expanded forms as a graph type, this gives something like that. Okay, here are some of the typing rules, and the one we'll be using to type these examples. The first one is witness elimination. Well, the idea, if you have, well, basically, if alpha 1 embeds the equation between tau 1 and tau 2, and M1 as type alpha 1, meaning that it is a witness of this equation, then we can use it to introduce the equation tau 1 equals tau 2 and use it to type M2. In practice, when you use it, we will use the GC rule, which allows to remove some kinds from the environment. The var rule relies on substitution to do the instantiation, and the app rule shows how you decompose a type in the kinding environment. So alpha is supposed to be an arrow type with domain alpha 2 and codomain alpha. So how does it work for detecting ambiguity? Let's see first for first example. Basically, what's happening is well, we've eliminated the witness, so we have the equation a equal int, and in this environment, in order to type if pos to the app rule, we are going to need actually to embed all those. So we need to add all these variables to k. But the GC rule allows to remove everything that is not accessible from gamma and alpha. Well, when I say not accessible, it's transitively from gamma and alpha. So actually all the internal nodes can be removed of the application. Not only internal rows of the applications, but also the first argument of x, which is supposed to be of type int, disappears in the result, since the result is just the type of the second and third argument. So the idea is that the second and third x are going to be typed as beta. The first x is going to be typed as something which is going to be ambivalent of a of int, but this we can remove with GC so that we finally can use the rule use to finish the derivation. On the other hand, if we consider a minimal derivation for G3 in this, which is an example corresponding to the problematic example we were describing, what happens is that, well, we are adding here the equation a equal into int, and we are typing g of 3. But the problem is the result of typing j to 3 then needs to be an ambivalent type of int and a.cod. And since this is the real type, we cannot remove it with the GC rule. So the ambiguity is staying around, and this is going to be rejected. Now to our code development. It is based on a certified implementation of ML with structural polymorphism on recursive types, a work I did a while ago, which was itself based on Arthur Scherger's development using locally nameless cofinite quantification. We've been careful to make it manageable, for instance, by avoiding unification in type system by interpreting Q as the set of its rigid unifiers. And well, other clever choices. And as a result, we could eventually finish proof of subject reduction for the following rules. Well, the first three ones, beta, let, and delta, are traditional. But the other three are more unusual. In particular, these two ones are about decomposing type annotations, something you don't need usually in type system, where type annotations can be discarded. But here, since our type system is specifically one which is intended for inference, if we discard type annotations, the derivation will no longer be valid. So we need to keep the type annotation. In this case, it's easy, decompose the one on the argument and the result. But if this is a rigid type variable which happens to be equal by an equation somewhere else to an arrow type, then we need syntactically to decompose it. And this can be done, as we explained, by annotating the argument as our DOM and the result as our code. Last, if we have a trivial witness, it happens that we can actually remove. So, what is the relation of all that to principality? Well, subject reduction and principality are independent properties. So for ML-like type system, principality is rather a combination of two properties. One is monotonicity, the fact that the type derivation is still valid using a stronger typing environment where types are more polymorphic, and the existence of a most general unifier, which means that unification of types is going to admit a most general solution. An interesting remark here is that, for instance, the outside-in approach in GHC is not monotone. So we can say that actually that type system actually is not strictly principal. It enforces that the derivation are principal, but the type system itself is not. So this is completely unrelated to subject reduction. However, the existence of MGU relies on the ability to decompose types, which is also exactly what we needed to prove subject reduction for annotated applications, explicitly in that case. So while subject reduction in itself says nothing about principality, the mechanisms we added to the type system to do that are the ones that will allow unification to work. And it's actually surprising that we didn't realize from the beginning that the way unification was doing was deficient. So what remains to do? Since we work on subject reduction, you could think proof type soundness. However, actually, using this type system to prove soundness is not a really good idea. One problem we have actually is that the rule for the introduction of rigid type variables does not really commute with the other reductions. So we need an explicit type system to prove soundness. And if we're going to prove to use an explicit type system, translating into a more classical one is probably the way to go. Actually, there are already some formalization of type soundness of GADT described here. The other one, the one we think is also essential, is to prove principality. This is hard. A first step is the existence of most general unifier, and we said we think we are in good position to do that. Last, there is also the soundness of type inference as another role of Untitled to ensure that. It would be interesting to prove it not only for the type system we described here, which is explicitly geared at principality, but even for non-principal versions of the type system, because maybe it will allow us to see that even if there is a bug of principality in OCaml, this doesn't cause a bug in soundness. Actually, the bug we have described today seems to have no impact on soundness, because it doesn't change the detection of sharing. So further applications, graph types are also used inside OCaml to enforce the principality of first-class polymorphism of first-class modules. So here is an example for first-class modules. If you define this way a function that takes a first-class module of such a signature and then unpack the first-class module as an explicit module and apply it, this is typable, even though we didn't write the signature directly at the point we unpack, because the information on the annotation is propagated to the use point. On the other hand, if the information comes from somewhere else in a way that is not deemed to be principal, this can be detected and you get a warning. And the basic idea behind that is that the type is known if it is not shared with the type environment, which is exactly the same technique I've described for ambivalent types. So the extension should be, at least in theory, straightforward. In practice, many lines of code. We've also been investigating other approaches to soundness. And how to make OCaml type inference more robust. One is a direct approach by making the internal structures of the OCaml type checker abstract and having unification follow precise laws. Well, ultimately, the idea is that the type inference algorithm should look like its formal definition. And we've been making some progress, at least to make unification be closer to its logical counterpart. This is joint work with Takafumi Saikawa. Another one is indirectly by translating the type annotated source tree, which is the result of OCaml type inference, into Galena programs in Coq and relying on Coq's type soundness to guarantee OCaml's type checkers correctness. So this is actually a way to guarantee that each type check program was correctly type checked. This is not a general check on the type checker itself. But it is interesting to have this kind of double guarantee. The description of those can be seen on this page, and also where is also the description of what I talked about today. Thank you very much. I'm ready to take questions.